is indefinite integrals and the substitution method. Now, since any two antiderivatives of f differ at most by a constant, when we find a derivative and there are no bounds, that's called an indefinite integral. When we take the antiderivative, we end up with an antiderivative plus some constant c. Okay? We know this. We've done this. We'll continue to do so. Where c can be any arbitrary constant. Because if we were to take the derivative of this, we would end back up with this. Right? Okay. So that's just what an indefinite integral is. Now, I'm going to introduce a new rule for integrals. It's called the substitution rule, and it comes from the chain rule. So it's kind of like the chain rule for integrals. But there's such negative connotation associated with the chain rule that I don't call it that. I just say it's substitution. But you can use the chain rule to prove this and actually do that in your book. And if you want to look over the proof, you can. This is valid. Been used in a long time. What this means is you can find something to let u be equal to. And we're going to practice a bunch of these today. If we let u be equal to a differentiable function g of x, then du, our differential for u, is equal to the derivative of x and then the differential for x. So that's where this part right here got traded out for the du, because that's what we said du was equal to. And we said u was equal to what's underlined in red there, and we replace it. So we take something that looks like this long, complicated integrand, and we can simplify it. And substitution makes integration much easier. Okay? In this first example, I tell you what to let u be equal to. That will never be the case in the rest of the course. All right? So in this problem, if we let u be equal to what's being raised to the 7th power, then what's our du going to be? 8 dx. There's your differential. And look at what we have. There's our 8 dx. So when I rewrite this problem with the substitution in here, I can come up with the integral of u to the 7th du, because I had all the parts necessary for my du. Do you see that? Du is 8 dx. There's the 8. The dx, that got swapped out for the du. Now this I can integrate using the power rule. So by using the power rule, when we integrate this, we end up with 1/8 u to the 8th plus c, correct? But I don't want to know what the integral is in terms of u. I want to know what it is in terms of x. So what we do is we go back and we plug in what we said u was equal to. And what was u equal to? 8x plus 32. So we swapped it back in. Just to... Why did we find du? All right. We needed to find this because we needed to make sure that those parts were necessary. Find du. So you know what to substitute. For dx. You're going to see a lot of stuff today. So this is a first example. Don't ask if there's ever going to come a time that we do something. We'll probably, at the end of this, I think I have like 10 examples here. All right. So then once we found what du was, we simplify the integrand. By substituting I think I got too many t's in there, but we'll okay, by substituting u's and du's for the x's and dx. Okay? Then we integrate. Or find the antiderivative, means the same thing. And then we put the x's back into the problem. By substituting. Again. All right? So it's written out clearly. Any questions about anything that we've done in this process? All right? Example 2, I don't tell you what to let u be equal to. So we've got to determine. Here's a hint. You usually want to let u be the most complicated part of the function that you can get rid of. Yeah, we're going to let u be 7x minus 1. What is du equal to then? Huh?
Oh, yeah,
because when I take the derivative of that, yeah, see, if you let u be the entire square root, then when you find the du, it looks worse than what you started with. So try and see what happens. If you end up with something more complicated, you didn't pick the right thing to substitute. Typically, you want it to be the most complicated thing. The most complicated thing I see here is the square root. And if I let u be what's under the square root, then when I take the derivative, I have 7 dx. Well, look, there's the 7 and the dx. By the way, it's not always going to be this nice. Okay, so now we need to rewrite this problem, and this becomes the integral of u raised to what power? And we had our du, that took the place of 7 dx, right? Okay, now let's integrate this. We add 1 to the exponent. That becomes u raised to the 2/3. Yeah. It's 2/3 u3 over 2. You divide by 3/2, and that gives you 2/3 u to the 3/2 plus c. But we don't want to know what this is as a function of u. We want to know what it is as a function of x. So what's our final answer going to be? 2/3 times. And if you forget the plus c, it's going to cost you a point. Okay? Just saying. It's kind of important. When you put the plus c, you know that you had an indefinite integral. Okay?
And you would rather us not go ahead and factor these out?
No. Leave it like that. Okay? Example 3. What might we let u be equal to here? Here's a hint. When you take the derivative, the power is reduced by 1, right? So if I let u be a power of x, or x to a 4th power, when I take the derivative, I end up with x to the 3rd power. Let u be this expression down here that's being squared. So we're going to let u be x to the 4th plus 1. du is 4x cubed dx. Well, look at what we have here. There's our 4x cubed dx. How convenient. So when we rewrite this, then we have the integral of u raised to the -2 du. Now we just integrate using the power rule, right? Power rule says we do what? Add 1 to the exponent. When I add 1 to -2, I get u to the, and divide by. So this is going to be equal to -1 over u plus c. And our final answer then is -1 over x to the 4th plus 1 plus c.
So that's nothing, why did we divide by -1?
You add 1 to the exponent. The power rule is you add 1 to the exponent and then divide by the new exponent.
Oh, that's the derivative one. Okay.
Yeah, don't confuse the two.
Yes, yes.
Because we are still having to take derivatives here. We gotta,
Right.
you can't forget anything and don't get it muddled.
Yeah, right.
Just saying. Okay. This one's a doozy. The secret is picking the right thing to let u be equal to. Absolutely. I'm going to write this as x to the 1/2. Are y'all okay with that? So what is du going to be? It's 1/2 x to the -1/2 dx. So du is equal to 1/2 times 1 over the square root of x dx. Well, I have the 1 over square root of x dx, so what do I have to do? What am I going to substitute in? 2 du is equal to dx over the square root of x. If I take this and I solve it for what I have, the square root of, I'm sorry, the dx and over the square root of x, if I solve it for what I have, this then is the value that I plug in place of what's circled in red here when I do my substitution. So when I rewrite this integrand, what I'm going to have is the integral of u to the 1/3, sorry, u to the 1/3, but in place of the dx over the square root of x, I'm going to plug in 2 du. This is just 2u to the 1/3 du, right? Well, I can pull that constant out of an integral. We have a rule that says we can. Wow, that doesn't look like a 30. And when we integrate this, we get 2 times what? U to the 4/3 divided by 4/3. Well, that's going to be 3/4. Add 1 to 1/3, and what do you get? 4/3. Right? It's the power rule for integration. You add 1 to the exponent, and then you divide by the new exponent.
Can you explain that 2du again?
Yes. Whoops. Yes. What we did was, once I got my differential here, I rewrote it without the negative exponent. So let me just pull this off to the side. I have all right, I'm sorry. Let me start over. There's a step that I could have written, I guess, here, and that is du is equal to 1/2 1 over the square root of x dx. You're okay with what we got there, right? In order to get that that dx over square root of x by itself, I have to multiply both sides of the equation by 2, right? Because that way these 2's are going to cancel out, and that's where I got this, oops, that's where I got the 2 du from.
So you had to multiply 2?
Yeah, I multiply both sides. It's just solving an equation for what you want. I'm not trying to like get x by itself. I was trying to get dx over the square root of x by itself. So I did. I got dx over the square root of x. If this is bothering you, writing it like this, you can write it like this, 1 over the square root of x dx. It's the same thing.
No, that wasn't what was bothering me.
Okay.
I was just trying to figure out how you got 2du.
Well, that's how I multiply. Yeah, I got the 1/2 out of there because I did not have a 1/2 here.
Okay.
When you got use the third,
U to the 1/3?
use the 1/3, it's not half. I keep wanting to do where it says let u be 1.
That's what u is equal to. I said let u be this. Well, that's this.
Yeah, I keep
Well, quit wanting it if it's not right.
Well, I'm just saying, I wanna know why it's not that, and it's just because it's in there.
Because, why is it to the 1/3? Because that's what this thing that we let u be equal to, that's the power it was raised to. So this u is going to be raised to that power.
X to the 1/2 and the u is only getting rid of the
Yeah.
root symbol.
Yeah.
Oh,
We didn't want to let u be x to the 1/2 because that would leave us 1 plus u raised to the 1/3 over, well, over nothing. Yeah, it'd be 1 plus u raised to the 1/3. And we still have that problem with the 1 plus u inside being raised to the 1/3 power, and we'd have to do another substitution. Now, you can do multiple substitutions, but keep track of your variables. You'll have to change your variables. And typically, we go from a u to a v to a w to a, if you have to do multiple substitutions because it still looks bad. And you have to do all the back substitutions necessary to get back to where you want to be. All right, so we're not done because we don't have this in terms of x. So this is going to be equal to, just carrying over to the next line, 2 times 3/4, which is 3/2, u to the 4/3 plus c. But when we go to our x, this is going to be equal to 3/2 times 1 plus the square root of x raised to the 4/3 power plus c. Now here, I don't care if you write x to the 1/2 if you don't want to write the square root. I'm fine with that. I know what you mean. And I grade each of y'all's tests individually, one problem at a time, and look at everything, so it's okay. All right, example 5. What might we let u be equal to here? 2x squared. Here we're going to let u be equal to 2x squared. And I'm not writing this down for my health. When you go back and you look at my notebooks from when I was a student here, anytime I solved a problem, I wrote let u equal, and then I showed the work where I did the du equals, and then I don't have an x dx. I mean, I have an x dx, I don't have a 4 dx, so what do I have to do here? 1/4 du is equal to x dx. I show all this work on my tests, on my homework, everything.
Talk me through it again.
Okay.
Why are we not using the sign in our u?
Because I know how to integrate sine.
Okay.
I can integrate sine of x.
Okay.
But this angle is complicated.
Okay.
So we take the most complicated piece to work it down to something simple, which is why when we rewrite this, this is going to become 1/4 because the x dx that x dx got replaced with 1/4 du sine of u.
Okay.
And I can find the antiderivative of this. By the way, the constant can come out. And this is going to be 1/4 times negative cosine u plus c. Remember, when you take the derivative of sine, you get a positive cosine. When you take the antiderivative of sine, you get a negative cosine. You got to remember all that and keep it straight. All right, but we don't want the final answer to have a u in it. We want the final answer with an x. So this is going to be equal to 1/4. Actually, let's make it negative 1/4 cosine of 2x squared plus c. Okay? Not so bad. Okay, be careful. You have to select the proper thing for you.
X squared?
This is tangent squared x, secant squared x. What's the derivative of secant? Secant-tangent. We don't want to let u be secant because when I do the du, I have a tangent squared I got to get rid of. Okay? So let's let u be tan x. What is du? secant squared x dx. You've got to be careful in what you choose for u. And if you start out, let's say we would have let u be secant x, and then du was secant tangent. We could have done that, but then we'd have a tangent x left over that you don't want to mess with. So that would, we'd work ourselves into a corner and still not be where we need to be. When you integrate, you cannot have functions of x mixed with functions of u. It's all x or it's all u. You can't mix it until Cal 3. Okay? And then you do different things. So I'm just kind of giving you a foreshadowing of what's to come. English term. I've been doing a lot of English terms lately. Okay, so when I rewrite this,
Being interdisciplinary.
Oh, yeah, that's it. Okay. No, I've been helping my junior high kids with
okay.
English homework, quizzing them over terms. So anyway, how do I rewrite this? This is going to be u squared du. Because this whole thing right here was du. And we just replace it. And in place of the tangent, I plugged in a u. Tangent was squared, so u is squared. So when I find the antiderivative of this, this is going to be u to the third over 3. So this is going to be 1/3. I guess I should write it in the bold red because it's my final answer. This is 1/3 times, I don't need the parentheses there, not tangent x. Okay? Not so bad. All right. Y'all need a break? I'm sorry, I should have asked before. Let me pause the recording. Yes. Okay. Example 7. Looking at this problem, what might we let u be equal to? I agree. Let's let u be equal to 4 minus x. That way we can integrate the square root of u. Right? Well, what do we get when we do du? Negative dx. Okay? But I don't have a negative dx, I have a positive dx, so I'm going to replace that dx with negative du. So that's what I'm going to plug in for dx. This is what I'm going to plug in for u. What about that x right there? We have a problem. Well, sort of, not really. I just got to write that x in terms of u. So I have this equation right here, u equals 4 minus x. Well, can't I solve this equation for x in terms of u? So if I add an x to both sides and subtract a u from both sides, I get x is equal to 4 minus u. So when I rewrite this problem, by the way, that's what x is going to be, 4 minus u. I rewrite this as the integral of 4 minus u times u to the 1/2 du. Oops, I need a negative. I'm going to stick it on the outside. Are y'all okay with that?
That'll work.
Because eventually that's where it's going anyway.
Okay.
All right? So, to simplify this integrand, algebraically, we're allowed to distribute that, aren't we? So this becomes then negative integral of 4u to the 1/2 minus u to the 3/2 du. You see what we did? We just distribute that u to the 1/2. And we've simplified this because remember, the integration distributes across addition and subtraction. So we integrate a term at a time, and we're going to get, I'm going to keep going down, not across. Let me move this down. We get negative 4, okay, when we add 1 to 1/2, we get u to the 3/2. The 4 is there, and we divide this by 3/2. minus u to the 5/2 divided by 5/2 plus c. Well, I got to clean all this up because it looks really bad. So this is going to be negative 4 times 2/3 is 8/3 u to the 3/2 minus 2/5 u to the 5/2 plus c. Well, if I distribute that negative across subtraction, won't I get, yeah, well, I'll get 2/5 u to the 5/2 minus 8/3 u to the 3/2 plus c. Because when you distribute the negative, you change the signs. That positive became a negative, so I moved it to the back. And the negative became a positive, so I moved it in the front. My final answer then, writing this all in terms of x, is going to be 2/5 4 minus x raised to the 5/2 minus 8/3 4 minus x raised to the 3/2 plus c. And the ta-da was deserved. Very good. Any questions? It looks horrible until you get into the process, and it's really not that bad. You decide what to let u be, find your du. You solve so that you have what you need to substitute. That would have been bad. That should have been a dx. Yeah, well, you should have spoke up. Sorry. Sorry. All right. The mom and me came out there. I'm sorry.
You're fine.
She has a mom.
My mother does.
Okay. So, yeah, but I'm your teacher. I shouldn't do that. So this is the dx's by itself. Get the dx, do your substitutions, simplify the integrand algebraically, integrate a term at a time, put the x back in the problem, and you're done. Ta-da!
Make it a song.
No, I don't. No. There are songs out there for calculus on YouTube. Just Google them. All right. Example 8. What might we let u be equal to here? I agree. I'm going to let u be equal to x cubed plus 1. Du is equal to okay. I don't have a 3x squared dx. What I have is 3x to the 5th. So I'm going to take out the 3 and the x squared with my dx. And what does that leave behind? X cubed square root of x cubed plus 1. What can I plug in for that x cubed? Because this part is going to be eaten up with the du. I can solve this right here for x cubed. X cubed is equal to 1 minus u. So when I set up my integrand for my problem, it's going to be the integral of u times u to the 1/2.
Get the minus u from?
Oh, my bad. You're right. I screwed up. It's going to be, yeah, that's what I meant. It's going to be 1 minus u times u to the 1/2 du.
Doing the same thing.
Did I?
Yeah.
No. 1 minus u is our x cubed. And then there's the u to the 1/2. And what's underlined in red was my du. Yeah, I only make a mistake once per problem, per line. I try to catch them. But I have you guys to keep me honest. Now we distribute. And we get the integral of what? U to the minus U to the du. So let's find the antiderivative of this. This is going to be U to the minus U to the. So I'm going to carry it a step further. I'm going to take care of that flipping of the fraction thing and replacing the u's with x's all in one fell swoop here. So this becomes 2/3 x cubed plus 1 raised to the 3/2 power minus 2/5 x cubed plus 1 raised to the 5/2 power plus c. Okay, so there's our final answer. We rock. We will pull this one up and be humbled.
You really say humble?
Yes. Houston. Humble is down there, north of Houston. Okay, what might we let u be equal to here? Ooh. Okay, let's try it. If we let u be equal to e raised to the sine squared theta, du would be e raised to the sine squared. You already see the problem, right? We don't have another one of those. Yeah, so that's not going to work for you. But hey, we tried. What about what? Sine squared theta?
Well, but then we,
So du is going to be equal to, chain rule, 2 sine theta, cosine theta, d theta. Well, now we're on to something. Because guess what? This is equal to this, because that's a trigonometric identity for the double angle formula.
That's not what you say, that's not sine
that's
squared.
what I was looking at.
All right, rewrite this using the parentheses, the powers. So this is sine theta squared. And when you take the derivative, you use the chain rule. Bring the 2 down, leave the inside alone, then multiply by the derivative of what's on the inside. We have a trigonometric identity, the double angle formula for sine, that says sine 2 theta is equal to 2 sine theta cosine theta. So guess what? We have everything we need for d theta. So when we rewrite this horrible looking problem, it becomes the integral of e to the u du. And what do we get when we integrate e to the u du? E to the u plus c. So this is going to be e to the sine squared theta plus c. Looked really bad, not so bad for real. Okay?
I'm glad you remembered to take off the top of your head.
I teach it. That was the last problem. I thought I had 10. I guess we're done.